Well, hello and welcome to the Institute of Science and Technology's AI Special Interest Group online seminars, introduced by me, Richard Saldana. These seminars aim to explore a wide range of AI-related topics with invited experts, everything from algorithms to ethics, explanation and trust. It gives me great pleasure to introduce Dr. Jay Flynn from Swansea University to you today. Dr. Flynn is a machine learning engineer whose primary focus is the automotive industry. His research covers anomaly detection, computer vision, predictive maintenance, layout optimization, and many other machine learning methods. As electric vehicles emerge as the dominant form of green transport in the UK, it's essential that effective infrastructure is in place to support their uptake. In today's seminar, Jay will present a novel approach to automated surveying of the built environment using deep learning and geospatial analysis. The aim is to identify residential properties suitable for electric vehicle charging. This methodology can be applied in a wide range of situations across various industries. I look forward to listening to a very informative seminar. Jay.
Thank you, Richard, for the introduction. So I'm Dr. Jay Flynn, and I'll be going through exactly what Richard has described. I'm going to be talking to you a bit about how we can automate mapping electric vehicle infrastructure. Now, to get straight into it and to sort of show what I'm going to work towards today, in the next half hour, 40 minutes, I'm going to show 4 years of research that led us up to producing this single image. Now, what this image shows is a survey of about 4,300 homes in a location in the south of England. And you can see every property is highlighted here, either in yellow for properties that are suitable for home EV charging, or black for those that aren't suitable for EV charging. Now, this represents a major milestone in both automated surveying practices and also understanding our EV charging infrastructure. And what's most exciting about this is that we were able to produce this image and do this survey in about 45 minutes. Current approaches to do this would take about 2 weeks. So really, really big step. And what I'm going to show is all of the research that has led us up to producing this. So in the next 35 minutes or so, I'm going to go through a bit about the motivation of this research, what the key stakeholders are, what other work has been done in this space. I'm then going to talk through the methodology of how we produce this image that I've just showed you. And then I'm going to give a quick sort of high-level demo, end-to-end, walk you through all the steps that we did to produce this in a short 5 minutes in PowerPoint format. And then finally talk a bit about the challenges and opportunities for future research. And I've given this talk a number of times in the past, and there's always a lot of interest in this. And so I'm going to try and save a bit of time at the end for questions as well. Okay, so first, a bit about motivation and prior research. So everyone can see that electric vehicle cars are emerging as the dominant mode of transport in the UK, and beyond the UK. But a huge barrier to the widespread adoption of these technologies, these products, is a lack of an effective EV charging infrastructure. Now, a lot of the academic work that's been done in this space are papers like this that you can see here, focused on a very large scale of entire nations, looking at optimizing fast charging points across journeys that might be like 100 miles plus. This is where most of the research is focused on mathematical modeling, optimization, optimal placement of fast charging across a very well understood highway infrastructure and a very well understood location of where petrol stations are and existing places where we could install this. Now, what we wanted to focus on is not the larger scale, but the small local area. Now, 80% of electric vehicle charging happens at someone's home in some form of off-street parking, either a garage or a driveway. These are the kind of properties that are suitable for EV charging at home. However, we currently don't know how many properties in the UK are have either a garage or a driveway. Even the largest mapping organizations like Ordnance Survey can't provide data on houses that have off-street parking, making them suitable for electric vehicles. And this is the gap that we aim to address in our research. So who cares? Who cares about what properties have a garage or a driveway? Well, understanding the home EV charging infrastructure is really important, firstly, to district network operators. These are people who manage our national grid, and understanding in the future where we're going to have a high density of cars being charged at home overnight is really important to be able to manage future grid capacity. In addition to district network operators and the national grid, local governments also have a keen interest in this. There's very ambitious clean air targets that local governments have to meet, according to the Paris Climate Agreement, European Green Deal. And one really effective way of meeting these targets is by increasing EV ownership. And one way that local governments can do this is by installing public electric vehicle charging. If you know the locations where people can't charge a car at home, then you can identify the optimal places to install these public charging infrastructures. And finally, of course, the automotive industry, by supporting a surveying approach to identify the EV charging infrastructure gaps, helps the automotive industry by selling their products, identifying consumer trends, and targeting marketing to certain areas, again, to support this transition to net zero and these Green Deal objectives. So I'm not going to go too much into the related research. I've put a few references to key sources that helped guide our research. I'm going to go a quick high-level overview of what these main papers focus on. Now, there has been some prior works to identify building characteristics and external characteristics of buildings from a range of data sources like satellite, aerial, and street view. And almost all of these approaches use convolutional neural networks. I'm sure many of you are familiar with CNNs, but if you're not, what a convolutional neural network does is it allows you to provide a neural network with thousands of images of labeled instances of data, like labeled instances of garages, driveways, residential buildings, churches, and the network can extract the features associated with each of these classes. Then if you show it a new image, in this case of a church, then the network has already understood the features associated with a church, a big pointy thing on a top and a cross. And therefore, it can say with a high likelihood, the image that you're showing me has the characteristics of a church, it's probably a church. And this approach is used by all of the papers that we reviewed to identify characteristics of buildings. Now, in our case, like I said before, we're interested in identifying garages and driveways. The problem that we face here if we want to use satellite and aerial imagery is, firstly, satellite imagery has a resolution at best with a bit of resampling of about 3 meters. If you want to identify driveways, the minimum driveway size is about 2 by 4 meters. So at best, you're going to get 4 pixels to do your image classification, which is just not enough information to be able to accurately determine if a driveway is there. Also, if you're looking from overhead, then a garage is very difficult to identify because you can't see that big characteristic blank door. Now, if you want to use aerial imagery, you get a much better resolution, but it's not scalable because it's so expensive to get this high quality image data like you can see on the right. So because of this, we wanted to focus on street view data. That is street level data taken at eye level. And those 2 paragraphs we've managed to put in a paper and get a paper out of explaining why you can't do this. And I've put a reference to that there. So what I'm going to focus on for the rest of this presentation is how to identify garages and driveways in Google Street View. So again, high-level summary of the gaps in the literature review. There is no previous work that's been done to identify driveways in any sort of data. There's no previous work has been done to describe a fully automated approach to survey a city using Google Street View data. And in fact, there's no real approach in the literature that we could find to perform a comprehensive survey of any kind of the external characteristics of buildings. Those that do exist are mainly aerial and satellite imagery. If they do incorporate Street View image, then you're going to get maybe one image per street at best. A notable exception to this is a report by a company called Field Dynamics. Now, this was not an academic piece of work. This was a report published by an analytics consultancy as part of some marketing and advertising. And that's what you can see on the right-hand side here. So this was an image where in GIS, that's Geographical Information Systems, they look at satellite and aerial imagery, and they essentially measure the distance between the pavement and the front of the house. And if there is a gap big enough to park a car, then they say there's a driveway there and it's suitable for EV charging. And they've surveyed large areas using this approach. Now, they don't include much of a methodology of how they do this. They don't describe exactly how automated this is. But to highlight an issue with this approach, I've got an image here. So you've got a few houses here, and it looks like on the face of it, all of these houses would be suitable for EV charging, right? You pave over your grass, maybe you knock down a small wall at the front, and you can park a vehicle there and charge it. If you look from the street level, however, this is what you see. So suddenly it's not looking very feasible to install a driveway here, at least without considerable expense to the owner. So we are not treating these cases as suitable. Maybe if you're looking 30, 40 years down the line and a lot of investment potentially, but we disregard this approach. So our research objectives, therefore, are to produce a scalable methodology to survey residential areas for all houses suitable for installation of home EV charging units. So we're excluding commercial properties from this research, just focused on residential. We're just looking at properties as well, not households. So if there's 4 families living in a flat in what looks to be a residential property, we're treating that as one house. If you were to do that, you'd need additional data from the English Housing Survey. We did reach out to them, but we didn't get a response. Finally, we're only considering integrated garages and driveways. So if you have to walk like 5 minutes around the corner to your detached garage, we're excluding that. And finally, as I just said before, we're only looking at properties that are immediately suitable for EV charging installation. Like this image here, we're not including images where you have to bulldoze a significant area and invest 10 grand to park your car. Okay, so quick time check. Now that I've gone through the sort of the why, I'm going to move on to the how. What was the methodology that we did to achieve this? Now, there's a lot of information here, and I'm going to break this down over the next 5 minutes. So the way that we approach this automated surveying is to break this into 5 steps. Firstly, we use OpenStreetMap data to get all of the coordinates for our survey area. That's every single coordinate along the road network. For each of those road network coordinates, we then get the associated Google Street View images. That gives us images across the whole road network within our survey area that we can then pass through those pre-trained convolutional neural networks that I mentioned. And that will do the classification for us for each image to say, yes, it's suitable, or no, it's unsuitable. And we can use that information then to plot the map that I showed you right at the beginning. And that's a lot to take in. I'll break this down step by step. So first, let's look at step 1. Where do we get our data from? So here you can see a map of a small town in North Wales, Wrexham. And this is on here you can see a red dot where we're going to try and get our first Google Street View images. Now, this has been extracted into MATLAB using a very simple bit of code. And you can see on my X and Y axis, I've got this in longitude and latitude, which means that for every point along this road network, we can find the coordinate. We can send that coordinate to the Google Street View API, and that will give us back 4 images. And those 4 images are at different angles of where the Google Street car was facing: 0, 90, 180, 270 degrees. And that gives you like a full panorama. And we then repeat this for every single stage along the entire road network at 5-meter intervals. And this gives us full coverage of the entire town of Wrexham. Now, this approach seems effective at first, but a problem that we faced immediately is that a lot of roads in Wrexham, there's not a lot going on. Most roads are actually, there's no houses there at all. And we're just getting images of trees and fields and bushes, which isn't particularly useful to identify houses with garages and driveways. A much more efficient approach is to use GIS, geographical information software. So what this allows you to do is take very detailed information from OS maps, and then we can pass this through a range of layers that you get your graduate student who's helping you out to do. This is, thank you very much to our collaborators in the Swansea Uni Geography department for this. And then you can get all of the coordinates, not just of the road network, but of each individual property. And then we use these coordinates to, again, retrieve the images associated with each property. Long story short, we only have to get one, put through one request for each property, and we get a nice photo of the house. So these are the two approaches, and I go into detail about why each one of these are better and the pros and cons of each of these in the papers. The reason that the first one that I showed you is better is because it's all one code. It's all held in one place. And this allows you to just in one click hit run, and it will find all of the road coordinates, get all of the Google Street View data, do all of the analysis, and send you a graph. So single click, and you can do a complete, fully automated survey of an area. In comparison, if you want to do the GIS approach, then you need to find your grad student who's going to help you to do the initial work, to put the map together, give you the coordinates, and then you can click run. But as I said at the beginning, this is very quick to do. I found a grad student who was able to do this in about 20 minutes to get this information for a survey area once she understood the process. And again, we detail this process in the paper. Most significantly about the OS approach, however, is that OS data is really expensive. However, if you're contracting for a local government, then there are some licenses that will allow you to access that data. Working with them, it's called a standard form contractor's license. So although the data is not fully open source, there are means to deliver this work through standard license agreements. And the benefit of this is that it's much more efficient than the other one because you are being charged for every Google Street View images. And I will give a cost breakdown of this survey later on. So that's the data acquisition. Next step, image classification. So initially what we tried to do is just do a simple binary classifier. So with our CNN, we give it loads of examples of an EV suitable property, that is a property with a driveway or a garage, and then loads of images of an unsuitable property. But this approach didn't work well at all at first. Really low accuracies. It had no idea what was going on. And here's a few examples. Well, here's an example of why. If I was to ask you if the photo on the left contains a property suitable for electric vehicle charging, this is quite a confusing question. There's a dozen houses in this image. Some of them have driveways, some of them don't. It doesn't really make sense asking it at this angle. For the photo on the right, it's very clear that this house isn't suitable for electric vehicle charging. No house, no driveway. So we need to find a way of filtering out these images that look directly down the road or contain a dozen houses, so that we're only looking at photos of the correct view. And we took quite a novel approach to do this. We actually used 2 CNNs in a series. The first network acted as a filter. What we did here was basically anything that we didn't care about, like trees, car parks, and these views where you can see 12 houses, we had separate classifiers for those, and we ignore them. Anything that's classified as that, we leave it. We filter it out. Anything where you've got an image like I just showed you on the right, where you have a nice photo of the side of the house we pass that on to our second network that does this binary classification. And this approach worked so much better. So I think using this in our first testing locations, we were getting accuracies of like 93% plus. And this is a really efficient way to do this. The downside to this approach is that you need a lot of data to train an effective model to do this. And you can see here, we collected about 20,000 pieces of data from 6 different locations in the UK. Really important to get different locations because then you have a nice diverse training set with different architecture, different building styles. A garage is going to look different in somewhere like Swansea to somewhere like Wrexham. And we account for this by trying to make as diverse a possible training data set. Again, the downside to this is myself, my wife, and my graduate student had to sit down for 5 days and label 20,000 images. However, we did send a sample of our data off to a local GIS officer in a local council. They validated 200 images, admittedly a small sample, and they agreed with 98% of the data that we shared them. And we weren't just showing them photos of trees, we were showing them photos of houses that were either suitable or unsuitable for EV charging. So this validation sample, we believe that we have a sufficient quality data set to do this survey. So now let's look at the outputs of the model. So we've seen how we get the data from OSM and Google Street View. I've gone into a little bit of detail of the CNN. We use 2 CNNs in series to do this, the first acting as a filter and the second doing binary classification. I've talked a bit about where we get the training data for this and how we validated that training data. Again, 6 different countries in the UK, tested at 1 location. And now I'm going to show you the 2 case studies that we did. Sorry, 1 case study so that we don't overrun. So I'm going to give you like an end-to-end walkthrough. So that was a lot of information to digest in like 10 minutes of our full methodology. So let's go right back to the beginning to that first diagram that I showed you of the survey. And I'm going to go through each step of how we got this data and how we produced that image that I showed you at the start. So here is this GIS output from my lovely graduate student who spent less than an hour putting together multiple maps and identifying all of the residential properties within an area. Now, the reason for this funny shape is because this is a census output area. And you'll see in a minute why this gives us a lot of extra data that can be valuable. Now, using the coordinates of all of these properties, put that into our MATLAB code. And for each of those coordinates, we send off and we get the images from Google Street View using the API. The first CNN then filters out all of the images that are unsuitable, all of the ones that are looking at views that we don't care about, or looking at views of trees, because remember, we're downloading 4 images for every location. And when it finds the right one, it does the binary classifier. Is it suitable or unsuitable? And then it is as quick and as simple as that. Then we can plot those outputs, you give it back to your graduate student, who then overlays a new layer to her GIS map of the locations that are either yellow, suitable, or black, unsuitable. And here, really quickly, in like under an hour's of work, we've done a survey that before would have involved multiple GIS officers going around in a car with a clipboard and doing a survey of the local area, which will cost a lot of money and take a lot of time. And here we've done it sitting at our desks in half an hour. And it really is that fast to do. And this can be done for anywhere in the UK. Currently, we've only got it set up to do in the UK, but you give me a census output area and we could do this survey anywhere within 45 minutes. So really, really powerful approach. And this is not just applicable for electric vehicle charging. And we'll get onto this in a minute. You can repurpose this by retraining your CNNs to identify loads of different things about houses. Now, I mentioned the census area. Now, this green area in the top right, I've just taken a few bits of aggregate data for this area. So mean age, 38, household composition, 64% is a 1-family household, mean income, 45 grand, 45, sorry, 45% have only one car, 37% two cars. You can see how this information is so useful for an automotive company to identify if this is an area that is suitable for targeted marketing. Similarly, this is really useful information to understand, well, in 10 years, how many of these households are likely to be purchasing an electric vehicle? Again, very useful information for district network operators to understand how an area, how the energy demand for an area might change as EV ownership goes up. So this is why it was important for us to incorporate that census data. There's so much information that you can get out of this. Now, the really interesting thing is the cost. So the only costs associated with this are the charges that we get for each Google Street View image that we're downloading. And that is about $7 per 1,000 images. And you get quite a generous free amount from Google. So you could do a small scale survey completely for free within the free limits. And that's exactly what we did. This survey cost $87. Sorry, £87 when converting from dollars. Really, really cheap. And now if you would scale this up from a small town to a whole council, you can deliver a full survey of an entire council, in this case, Ashford Borough Council, for £1.5 grand. Extremely low cost approach to surveying an area. Now, that does come with an accuracy of, I think I glossed over it on a previous slide, an accuracy of about 87%. But there are things that you can do to improve this accuracy. This is just the first proof of concept of this. In some of our test locations, we got up to 92% accuracy. And still, when you're dealing with data, with this much data, that is still sufficient, we believe, to give an accurate representation in the future of what a whole community usage or uptake of electric vehicles will be. So I hope this has sold you on the power of this approach and how valuable this could be. And quickly, I will now flip back to this, what I showed you earlier, the pros and cons of both approaches. What I've shown you here is just the GIS approach. And I've talked a bit about the cost of OS data, but there's ways that you can prove this as well. At the moment, Google Street View has some associated costs, but we're seeing new alternatives to Street View come in, like Mapillary and Carter View, and these are open source and completely free. And that would get rid of the only cost associated with doing this survey. So even with an accuracy of 87%, if in 5 years, these emerging streetscape imagery sources are completely free, then in an hour, you could do a survey of a whole council completely free of charge. And this is possible right now for 100 quid. So that's sort of all of the meat of this that I was going to show you so far. And I hope I've convinced you that this is a really valuable piece of research. I want to talk a bit about the shortcomings. Now, on this map, you can see here in the bottom corner, there's an area where it says all of these houses are not suitable for EV charging. And you might say, well, a local council might look at this and be great. We might want to install some community charging points there so that people can still access these electric vehicles. Now, when we look a bit deeper into why these areas were classed as unsuitable, I've got an image here. My slides keep jumping to the next one, but bit of audience participation. Can anyone guess why all of these houses were identified as unsuitable for EV charging? You're welcome to come off mute and brainstorm. Why do we think these are unsuitable? And there's no driveways or garages in these, but some of the houses do have driveways and garages. I encourage you to unmute, and can anyone have a guess as to why these are not suitable for EV charging using our methodology? I will hint you towards the image on the right. What does this house look like to you?
Well, that's a show home, Jay.
That is a show home, isn't it, Richard? And you can actually see in the left-hand image, you can still see the lines where the graph was recently turfed. And this causes a few problems because it meant that Mr. Google Street View or Mrs. Google Street View hadn't managed to get round there yet. You can see in blue are the locations where the Street View car had reached. So unfortunately, all of our data for this area just said no data was returned. Thank you, Richard. So this is one limitation of this approach, right? This is only as good as the data that you've got. And there's a few issues with linking up the very up-to-date Ordnance Survey data with not so up-to-date Google Street View data. So there is some work to do here to understand, well, what locations are suitable, where has the most up-to-date Google Street View, and how we would maybe represent that in that graph that I showed you earlier. So where can we take this next? So in addition to improving the efficiency of this approach that I mentioned, one thing that I'm really excited about here is how transferable this is to other use cases. Once we have a scalable approach to do large-scale automated surveys of the external characteristics of buildings, this opens up so many potential avenues for future research. One example that we got a lot of interest about was identifying the energy efficiency of homes. There's a lot of external characteristics of houses that some research has already done, like you can see on the right, identifying architectural characteristics like windows, double glazing, the size of windows. This is really useful information to understand how energy efficient is a home. What type of roof does it have? What direction is the roof facing in comparison to the sun? Useful for solar. All of this information, you can create different data sets in your convolutional neural network to identify these characteristics. And again, survey how many houses in your area have double glazing, how many houses have a south-facing roof. So there's so much potential to repurpose this. And once you've got that underlying infrastructure set up to do this image classification, very easy to retrain your neural networks, provided you can find a grad student to label 20,000 pieces of data. So to summarize then, what would we do next? Firstly, improving the efficiency of the one-click approach. There are ways that you can use OpenStreetMaps to not survey houses, survey roads that are in the middle of the countryside. You probably don't want to survey motorways, not a lot of houses there. So there are things that we can do to improve the efficiency of this approach. And similarly, we can also do the same with the GIS approach. Maybe we don't want to just take one location outside the house and take a few photos from neighboring properties, get a few different angles. There's lots of work that you can do to improve the accuracy of both the data acquisition and the accuracy of the image classification. Secondly, let's find some areas where CartaView and Mapillary have got really good coverage and just do this survey for free using open source data and repeat this. I'd love to see someone do that because again, that opens so many doors for future research. And then we can share that code and anyone can have a play around with this. Because of the Google licensing terms, unfortunately, we were not able to share our data set. We did reach out to Google to try and publish this, but it's very, very clear in their terms and conditions that you can't go publishing 20,000 labeled pieces of data that we've essentially scraped from their website. Acceptable for academic use, but not beyond that. Again, really important reason why we need to be shifting towards CartaView and Mapillary. And finally, let's explore some other use cases of this. At the moment, I've got the blinkers on and all I can think of is energy efficiency for homes, but I'd love to see what other people think where you could take this and what could be surveys using this approach. Okay, so I said that I'd leave 10 minutes for questions at the end, and incredibly, I seem to have got that bang on. So I hope that everyone enjoyed this presentation. As you can see, this is something that I'm really passionate about. I think there's a lot of opportunities here for research in both the academic space, as well as some, I think, quite valuable applications commercially as well. So thank you so much, Richard, for giving me this platform to share this research. Thank you everyone for listening. I hope you enjoyed it. I encourage you to come off mute and ask any questions. Perhaps before I do that, I'll hand over to Richard to close.
Well, Jay, that's really great. Thank you very much. And I have got Murray Webster, who's got a couple of questions for you. And Murray, I suggest you unmute and ask these questions.
Grant, thanks very much, Richard, and thanks very much, Jay. Really interesting. I'm a member of the AI Special Interest Group here at the IST. We're always really grateful for these seminars, and I just think that the work that's going on here is absolutely fascinating. Really intersects with all of our interests, so thank you. So the couple of questions I had. So I was really interested in the way that you were talking about the desire for scalability in the methodology that you're using here. Given, though, that you had to categorize manually 20,000 images of garages and driveways in order to provide a set of training data for the CNN, how scalable is this methodology going to be for structures which are more complex and have more variety than garages and driveways, which tend to look fairly similar to each other?
So what sort of, well, firstly, the beauty of developing a data set is that you only have to do it once if it works. And once you've got that data set, it's there to stay. You can just improve on it, and you don't have to do it again. And there's a lot of ways that you can crowdsource, like with your Google Capture, and get people to support creating these data sets. So there's a lot that you can do to minimize the labor that goes into those tasks. In terms of identifying characteristics of similar buildings, and this is why we wanted a really diverse data set for what we've done. We got training data from 6 different cities because driveways and garages are quite similar, but things like how the front walls change, the level of greenery at the front of a house, the architectural style of a house, they are more diverse than you might think. But you're absolutely right. If you want to transfer this to other use cases, you are going to need to build a very detailed data set, and it will have to be a supervised approach. So I don't see any way around putting in the time and the labor to build those data sets. But the important thing, and I hope what I've conveyed in this, is that it's important that you do have a diverse training set. You do have a sufficiently large training data set, and you demonstrate that it works in urban locations, rural locations, to show this proof of concept. I hope that answers your question. I know I've referred more to the methodology than the technical solutions, but does that answer your question?
Yes, it does. Just one of these things that I was quite interested in, because obviously it seems to have so many applications beyond simply identifying garages and driveways. It seems it could do a lot of other things for houses, buildings, and sort of so many potential other applications. It was just when you said you had to categorize manually 20,000 images, and you think that's an absolute thankless task.
Yeah, it was a boring week.
Yeah.
What I would say is we did try to replicate this in France and do a survey in France and see how the performance varied. Like, if we use a training data set that was done in the UK, how well would our model perform without any retraining in France? Unfortunately, we weren't able to do that. But that's another opportunity for future research, right? How small a data set can you get away with? And if we use approaches like transfer learning, if you take it to another country, there are ways that you can transfer learn a neural network and just show it 10 images of what the buildings look like in that small area, and very quickly retrain your neural networks without having to go to the labor of doing a whole new data set for France. So there are a lot of approaches that you can get around this if you do want to scale it to other areas.
And this is one thing I was very interested in, taking it to different locations. I live in Sweden, I'm in Gothenburg. One thing that's very common here actually is that the city is fairly dense in terms of residential housing. Parking tends to be built underground in the basements of the buildings. And it would be kind of interesting to see, as it is in the building that I'm in, kind of interesting to see if you could design an algorithm to get around a problem like that, to design for EV charging in far more dense urban spaces where you don't necessarily have street view data?
So there are limitations of Street View, right?
Yeah.
You can only really find things that you can see from a street level and are clearly visible in the image. A big problem that we had was identifying driveways in very rural areas, because everyone likes to have big trees at the front of their garden, and nice hedgerows, which means that from a street level, we can't see the driveway. All we see is a load of green hedges. Or maybe someone's parked a van in front of the driveway. There's loads of reasons why what you're looking for might be occluded. And in the example of like underground parking, maybe there are signs from the street level, I don't know, maybe signs or some sort of diversion off the road where you would go into your underground car parking that might indicate that that's there. But these are what you need to be very careful to define when you're training your neural network. And I think when you're repurposing it, it's very important to have a very clear definition for your training data set, and not to deviate too far from that. That's something that we found very early on.
That's great.
Again,
Thanks very much.
I hope that answers your question.
It does. It really does, actually. It's fascinating stuff. I would have just a second shorter question, which would be about, I noticed in the top left you had funding from the European Union. I was interested in how your data storage methodologies comply with both the GDPR and the Data Protection Act. Richard is laughing. This is the same question I usually ask. Particularly when you said that some of the data that you had could be used for commercial purposes for marketing by electric vehicle companies. I'm just wondering what the kind of legal requirements were on the project.
We did spend a lot of time working with IP lawyers, data licensing lawyers, to understand the legality of what we're doing here. And it was a serious concern. And we found that for educational use, this is okay, based on what's been done before and the licensing terms. But this is why it's really valuable to look at these emerging open source examples, because there doesn't really seem to be any restrictions on using this. This is open source data, which is gathered by the community. And what you're viewing from a street view image is nothing differently from if you walked down that street in a public area yourself. So certainly to address these concerns, we need to move away from Google Street View. Their licensing terms are very clear. You shouldn't be doing this for commercial use. Mapillary, car to view, no problem. That is the solution to the GDPR and legal issues. But that's coming from me, a data scientist, and not a lawyer. So also find some legal advice for that one.
That's grand. That's everything I've got to say. Thank you very much, Jay. Really appreciate it. Thanks, Richard.
Thank you, Murray.
Thanks, Murray. Now, Joan Ward has a question. I think it's sort of related. You may have already covered this, but she's asking about factoring in apartment blocks with internal stroke external parking. And I think that's probably sparked by that image that you showed of the 5th arrondissement in Paris, because I mean that's a thankless task, I would say, and very few buildings have off-street parking, certainly.
So does Joan want to jump in there, or is that the question? How can this be repurposed for apartment blocks?
Yeah, I mean, I think I was just really interested in terms of the bulk of it is sort of domestic parking and how you can put charging at homes and things, and really how you would factor in the fact that there's in lots of areas it's big apartments, some of them outside parking, some of them have underground parking. So how do you factor all of that in when you're looking at home charging?
Yeah, so and this is why this is another really difficult one to answer, and this is why we kept it out of the scope of this research, is because to gather a data set to train on residential properties, it's a pain, but it can be done because there's loads of data available. If we were to build a training data set of just looking at residential flats, that is an incredible amount of manual work to go in and find those properties and find the right views where you can see how much car parking space is available. Again, if you can see those characteristics that would make it suitable from the street level, it can be done, and we and other research has shown that that's possible. The problem that you would have there, if you're looking at these sort of flats, is that there's just not as many of those that you can find the data for. You know, you drop a pin anywhere on Google Street View and you're either going to find a tree or a house. If you're randomly trying to find a suitable image for a training set for apartment buildings, you're going to be doing a lot more digging. And that was the barrier to including that in our research, because we just didn't have the time to build a training data set for it. And this all comes back to time and resource. I think technically it's possible. And maybe there's some approaches like transfer learning that would make this easier to do, but not a problem that we were able to solve here. Okay, thumbs up. I hope that answers your question. Good.
Jay, I've got a question for you. So, I mean, it's quite a general question, but can the UK national grid sort of support the level of EV charging that's sort of envisaged? We're being encouraged to buy electric vehicles, scrap our current vehicles, and you know, have you seen anything on the planning in terms of the amount, the volume of electricity that we're going to demand?
Well, firstly, I'm by no means an expert at all in areas related to national grid and electric infrastructure, but this was the motivation for this research, right? There's a lot of other research that's been done out there and information available in the public domain that shows this is a problem. This is why we wanted to do this research, was so that we can provide data to people like district network operators to support this growing challenge. I'm not in a position to comment on the severity of this challenge, but I hope that what we've shown here, in what I think is quite a thorough proof of concept of this, goes a long way in supporting this challenge within residential areas. I still think there's further research to be done here, but I hope through platforms like this, where we can share this research and show what can be done in this space, that we can help in addressing some of these wider challenges. Yeah,
definitely. I mean, if I was involved in sort of capacity management, I'd think this is extremely valuable. And the accuracy rates are great. I mean, 87% for, well, any sort of real world machine learning technique is excellent.
It's, and again, that's for probably our worst location as well. So that's for a rural location. When you go to more urban areas where there's less trees in the way, and you can get a better view of those houses, the accuracy goes up as well. So, and again, it's a real shame that we couldn't publish this data set, because I think a reason that we got such high accuracy is because we had a really high quality data set that we put probably like 6 months into developing. And that work, unfortunately, would need to be done again using open source data. But what we've shown here is that it is possible. And when it is done, it's highly scalable and you can do it really, really quickly. And I think if the right person sees this, I wouldn't be surprised if someone goes and develops a web application to deliver this, because I think there's so much value in here. I think people would pay to do surveys like this, especially if you can get the results in 20 minutes and you can deliver it for low cost. I think there is really a commercial business opportunity here for this.
Yeah, I think I agree. So do we have any more questions? People feel free to pop your hand up, unmute. I think that's it, Jay. People are being shy, but no, I thought the questions have been good. So I mean, thank you very much on behalf of the IST and the audience present. I thought that was a really interesting and very clear seminar. Really good. Thank you. And if you enjoyed this seminar, you might like to take a look at our istonline.org.uk website. And in particular, I'd like to highlight our brand new professional AI accreditation, both for existing IST members and for those of you who might be thinking about joining the IST. We are the first professional body in the UK to launch such an accreditation. So we look forward to seeing you at a future AI seminar. Thank you all for attending, and goodbye.
Thank you very much. Thank you, Richard.